Dr. Barboni's current work is focused by the characterization of risk prediction and assessment of fire-line intensity of fires in hydrological forests, natural areas, and urban interface areas and forests. Dr. Barboni, please.
I would like to the speaker that the time for presentation is 15 minutes and an extended time of 5 minutes to discussion.
Okay, thanks. The study I'm going to present here concerns the relationship between fire-line intensity obtained by calorimetry and timelines. This work was realized in the scope of Project FIRELINE, supported by the European Union of the Operational Program France-Italy. Okay. Let's see the plan of my presentation. I will present the objective for this study, the experimental procedure, the fire-line intensity, and finally we conclude by the relationship between the fire-line and the fire-line intensity. The aim of the present work is multiple. Firstly, we will propose a methodology to effectively measure the fire-line intensity of spreading fire at a laboratory scale based on the oxygen consumption, noted OC. To this end, a large-scale heat release rate calorimeter has been used that allows to directly measure the heat release by the fire front. Secondly, we propose a new relationship between the fire-line intensity and the flame length, measured with the large-scale heat release rate calorimeter. To this end, a methodology based on the theory vision was used to measure the flame length. Different relationship between the flame length and the fire-line intensity proposed by other research are also tested. Among these, the well-known Biran's formulation will be considered. The ultimate project is to make a risk index for the fighting forest fire. There are several methods to measure the fire-line intensity. Among heat at the laboratory scale, we can see a large-scale heat release rate calorimeter, which the relationship represents here, with Biran's formulation, where fire-line intensity is the rate of heat release per unit time per unit land on the fire front, is given by the relation, where IB is the fire-line intensity, H is the heat yield of the fuel, W is the load of fuel consumed in the active flame front, and R is the rate of spread of the fire. This relationship is valid at laboratory scale and is transportable at the field scale. Another way to measure the fire-line intensity is the flame length. It is this measure that I will develop in this presentation. Heat release rate measurement based on OC calorimetry were conducted using the newly installed large-scale heat release rate calorimeter, 3 meter times for 3 meters for the hood. This picture presents the open burning heat release rate calorimetry with a combustion bench inside. The mass loss rate is measured and the exhaust gas are analyzed for the composition, the temperature, the optical obscuration, and flow speed with a bidirectional probe. The exhaust duct flow profile is essential due to the accuracy of the oxygen consumption calorimetry measurement. In order to validate the whole installation and reduce to the incertitude, the calibration procedure with a propane burn is required. 3 species of vegetation were conducted in this test fire: Linus pinaster needle, Avena fatuostro, and Genista spines. Experiment fire were conducted under no slow and without wind for line ignition fire, and combustion bench located into the calorimeter wood. The table is an air-entrained concrete plate of 2 meters long and 2 meters wide, placed on a load cell in order to measure the mass flow over during the fire test. For the linear ignition, a small amount of alcohol and the torchwork and the flame torch were used. It is the property of the fuel, H, W. It is the load of the vegetation of 0.6 to 1.2 kilogram per meter power cube. The moisture constant was determined by drying the specie in oven at 16 degrees C for 24 hours. The ambient temperature and relative humidity range respectively from 18 to 21 degrees C and from 35 to 49% for the work test. The measurement of the flame length was realized using a stereo vision system placed in the front of position relative to the direction of the fire spread. It is the camera. The flame length is defined as the distance between the goal and the heighted 3D points. The flame length is defined as the average length of all length flame mass for the whole pictures. The pictures were taken every 3 seconds during the stationary phase. Now this mobile demonstration. It is this camera for measuring the height of the flame, the flame length of the head flame because there is no slope and no wind. The flame length is 55 centimeters. And display an example of the heat release rate curve for fire spreading across Pinus pinaster with a load of 0.6 kg per meter. The corresponding mass loss over time is superimposed of the heat release rate. For the whole experiment, we observe the first peak of heat release rate at approximately 40 kW per meter. It corresponds to heat released by the burning of alcohol during the ignition. Then, depending on the fuel load, we observe that the pre-steady state was achieved more or less quickly. During this interval times, we observe that constant rate of spread, constant rate of mass loss, and constant heat release rate. The fire line intensity measured by OC calorimetry range varies from 29 from Genestal to 86 kW per meter for Pinus pinaster. The flame line measure varies from 13.7 from genital spine for 60 from Pinus pinaster needles. We observe that the flame length and the fire line intensity varies significantly according to the species and the fuel load. The statistical tests were conducted by the ANOVA or Tuket test. These differences are due to the property of the fuel bed. The fire line intensity measured by OC compared to the fire line intensity measured by using Biram's formulation for the whole experiment. We can see that Biram's formulation overestimates the fire line intensity measured by OC. The ratio between both formulations given by the linear regression is 82%. Why this difference? Presents the quasi steady state and combustion efficiency is not taken into account. Two reasons may explain the difference between Biram's formulation and OC result. The first one is due to the methodology from Biram's formulation. The fire fronts remain quasi-linear during the fire spread, but exhibited a weak curvature of the flanks, and overestimate the burner load when the fire behind of the combustion bench. The second one is due to coefficient efficiency that is overestimated by Biram's formulation. Effective heat of combustion, relative heat, were realized for each test by dividing the total heat released by the total mass loss. The key heat combustion vary from 81 81% for Avatar Fatual Straw, 85% for Genista, 88% and 86% for Pinus pinaster needles. The difference is due to the burning process. Pinus pinaster needles and Genista spines were completely burning during the fire test, or there are some unburning for the test realized with a vanilla straw. The concept of FIRELINE intensity is shown by Biran. It is, but because of difficulty to estimate in the field the fuel consumed and the rate of fire spread, the authors have derived relationship based on a visual estimation of a fire front property, namely the flame length. Biran, in green, Nelson and Adkins, Thomas and Newman have proposed the following relationship between the flame length and the FIRELINE intensity. In blue, how result obtained by OC calorimeter. We observe that all these models overestimate the true value, the true FIRELINE intensity measured by OC calorimetry. These different are due of the different conditions for establishing the different equations. Thomas' equation was developed for zero wind and zero slope fire. Biran and Newman equations were developed from data collected during wind-hail fire. Nelson and Adkins' equation was developed for fire both the laboratory and field scale. This relationship between the FIRELINE intensity and the flame length is proposed by the research. The flame length and the FIRELINE intensity proposed by Barboni and Hall is equal to 180 times length for times flame length power 1.9. This relationship is valid for the range of experiments conducted in the present world under zero slope and zero wind condition in still air. We will realize a prescribed burning in Corsica with the condition wind 1.5 meter per second, relative humidity 41%, temperature 23 degrees C, and the load of the vegetation from 8 to 32% depending on class of dead and live fuel. The aim was to measure the FIRELINE intensity with the Biran formulation. For this, we characterize the vegetation. It was Genista. We measure the percentage of live and dead particles, the percentage of particle live, the percentage of particle size, 0 to 2 centimeters, 2 to 6 centimeters, and greater than 6 centimeters. The calculate the rate of fire spread in the range are 380 meters per hour, and the mass of unburned. Then we measure the flame length with the same systems of the theory region, is approximately 5 meters. After the result, we calculate the FIRELINE intensity according to Biran's formulation, including the combustion efficiencies of Genista. The result of the FIRELINE intensity is 4,150 kilowatts per meter. We compare this value with the FIRELINE intensity obtained by the flame length, and we show that your estimation is the closest. Thanks for your attention.
Okay, the floor is open for questions.